Today we are going to be looking at approximations. Approximations here involve rounding off numbers, either to the nearest unit or whole numbers, or to the nearest 10, or the nearest 100, or to the nearest tenths, nearest hundreds, and so on and so forth. We are going to take some hints looking at approximations, which I'll be looking at how to approximate to the nearest whole number, etc., significant figures, decimal places, percentage error. Now, rounding off of numbers. A. Round off to the nearest unit, tens, hundreds, etc. Let's take, for example, 27.496. This will be equal to 60 to the nearest 10. When you approximate it to the nearest 10, it will be equal to 60. This same value is equal to 27.5 if you approximate it to the nearest tenth. And of course, it's the same thing as 27.50 if you approximate it to the nearest hundreds. The nearest hundreds. And so on and so forth. I want you to note that to the nearest tenth is the same as the nearest 0.1 or 1/10. We look at significant figure. Significant figure. Let's take an example of that. If you are giving, let's say example A, the number 5978 will be equal to 5980 if you approximate to the three significant figures. 1, 2, 3. The next number after 7 is up to 5. And then you approximate that to 10 and add 1 to 7 to give you 8 and put down the 0. In essence, what we are trying to say is that numbers from 0 to 4 are rounded down to 0, while numbers from 5 to 9 are rounded up to 10. In other words, we say that these numbers are closer to 10 than they are to 0, while the number 0 to 4 are closer to 0 than the number 10. So normally when we are rounding up number, either to giving number significant figures, we put this one into serious consideration. Let's take another example B. We are given 0.05978 and they have to round this up to significant figures. In this case, these zeros that are the beginning of the number are not counted as significant. but they are part of the solution. So in other words, this will become 0.0. You cannot start counting from 5. 1, 2, 3. And then the next number is up to 5, approximately to 10. You now have 5, 9, and then 8, and that place will be 0. But remember that because there is a decimal point here, this 0 is no longer necessary. So the final answer should be 0.0598, corrected with these significant figures. Another example, say 59.78 to two significant figures will be equal to 1, 2. The next number 7 is up to 5. You approximate it to 10, and then of course put down 0, carry 1, add it to this to give you 60.00. And of course this is same as writing 60 to two significant figures, and these zeros are no longer necessary. Next is for us to look at decimal places. What I'm doing here now is to refresh your memory of these things. You're supposed to have known them, but we are reminding ourselves of what they actually are. Decimal places, let's take a look at one of the examples here, which says 47.465. In this case of decimal places, you start counting from at the end of the decimal point. So if I'm correcting this one to two decimal places, it becomes the 47 will be written first, then point 1, 2, 4, and 6, two decimal places. After that, the next number is up to 5. Approximate it, as we said, add 1 here to give you 4, 7 to two decimal places. And that's what you are supposed to do about that. Or you can say, okay, let me correct this to one decimal place. What will it become? 47.5 to one decimal place, and so on and so forth. We shall now take a look at a very important topic, which is percentage error. Percentage error. Let's look at percentage error. Very important. Percentage error. Okay. Under percentage error, as human beings, we are prone to make some errors, especially in measurement. And in order for us to cater for the error we have made, which must be within a range, we have to calculate the percentage error. An actual measurement can be maybe 5 centimeters, and you are asked to take a measurement. Take that measurement. You may end up measuring it as 4.45 or measuring it as 5.5 centimeters. This is what we are referring to as an error, and we wish to calculate the percentage error of that measurement. How is this done? Number one, we have that our error is equal to your actual value of the measurement minus the approximate value of measurement. Take note of that. Or we can also say our error is equal to the degree of accuracy. The degree of accuracy or approximation. The degree of approximation. Maybe to two significant figure or to one significant figure or to two decimal places. That is the degree of accuracy we are talking about. Will be divided by 2, and that will give you your error. We also have what we call the absolute error. We have said that in measurement it can be more or it can be less, but we are looking at the absolute error. The absolute error here is equal to the absolute value. Absolute value of error. What do we mean by absolute value of error? For example, if you have -2 and the absolute value of -2 is equal to 2. So we are talking about the positive value of your error. Whether it is minus or it is plus, we are interested in the absolute value. The absolute value of -2 is 2. The absolute value of +2 is 2. The third one is the relative error. The relative error is equal to the error that you have gotten or that is given all over the actual value. The actual value. The relative error is equal to the error all over the actual value. Number 4. Now, the percentage error. Percentage error is actually equal to the error all over the actual value multiply this by 100 all over 1%. This is the formula you will use to find the percentage error. You can see now that this is also equal to the relative error multiplied by 100%. Sometimes we have the percentage error to be equal to the error all over the measurement. Multiply this again by 100 all over 1%. This happens where the true or the actual value, the true or actual value is unknown. Is unknown. You don't know the true or actual value and you are told to calculate the percentage error. You will see examples of what I'm talking about shortly. I want us to note that in measurement, the degree of accuracy improves as the unit of measurement. As the unit of measurement decreases. In size. For example, 9-meter measurement has error of 0.5 plus or minus, and percentage error of 0.5 all over 9 times 100 over 1. and that will give you plus or minus 5.56%. But a 1.75 meters measurement has an error of 0.01 all over 2, which is equal to 0.005. And the percentage error to be equal to 0.005 all over 1.75 times 100 over 1. And when you calculate this, you have plus or minus 0.29%. You can now see why we said that the degree of accuracy improves as the unit of measurement decreases in size. I've given you the example. We are now going to look at problems involving approximations in general. Now let's take, for example, most of these examples I'm going to solve are adopted from past questions of various examination bodies. Number 1, evaluate 2.813 times 10 raised to the power minus 3 times 1.063 divided by 5.637 times 10 raised to the power minus 2. Reducing each number to 2 significant figures and leaving your answer in 2 significant figures. Solution. Because we are told to reduce each number to 2 significant figures, the first number becomes 2.8 times 10 raised to the power minus 3, and then the next number is 1.1, and then all over 5.6 times 10 raised to the power minus 2. And then, of course, you can write this in ordinary form. It becomes, if they're moving this point 3 places to your left, 1, 2, 3 decimal point, and then of course times 1.1 all over. Moving this again, you have 6. Now starting from here, 5, 1, and then 2 decimal point. Now you can use your calculator because you're allowed to use the simple calculator to carry out these operations. You can use that and then you get an answer. You can also cancel. Another way you can do that is you move the decimal point 1, 2, 3, and that will give you 56. Then move the decimal point there 1, 2, 3, that will give you 2.8 times 1.1. Again, you can still move the decimal point, watch me, 1 place here, so that will give you 28 times 1.1. And then you add 0 to this one. That is, you multiply by 10 here, you also multiply by 10 here. This 28, we cancel 28 is 1, 28 here is 2 and 0. So you are now left with 1.1 all over 2, 0. You can divide this by 2. If you divide here by 2, it becomes 0.5 and 5. And divide here by 2, it becomes 10. To divide by 10, you only just move the decimal point 1 place to your left, and that will be equal to 0.055. You have moved it this way, 1 place. Then you are supposed to write your answer. Say correct it to 2 significant figures. So if you correct it to 2 significant figures, this will be your solution. So the answer to this problem is 0.055. Even without using a calculator, you see how easy it was understanding how to move the decimal points. Practice this, and I think it will help. Example number 2. Evaluate 21.05347 minus 1.6324 times 0.43 to 3 decimal places. So we'll carry out the evaluation and then we'll correct our final answer to 3 decimal places. Solution. These are supposed to be trivial problems for many of us. Remember the rule of Bodman's in this case. Remember the rule of Bodman to solve this problem. So what do? You multiply this by that. So you have 21.05347 minus. If you carry out the multiplication, you will have the following values. To carry out the multiplication, you have 0.701932. Then, of course, you will subtract this from this, and then you have 20.351, and of course, 538. And they are told to correct your answer to 3 decimal places. So that is 20.123. The next number to that is up to 5, so that becomes 3, 5, and 2. You will have done the problem, solve that, and that is correct. Number 3, we can also take another number. It simply says express 1, 2, 3, 4, 5, 6 to 3 significant figures. 3 significant figures. So express that to this significant figure. Solution to this problem is quite simple. 1, 2, 3, 4, 5, 6. Now you can 1, 2, 3. So the next number is not up to 5, so round everything down to 0. So this actually becomes 1, 2, 3. Many of us will leave the answer like this, and it is wrong. So remember, this are the zeros here. There's no decimal point here. So the correct answer is 1, 2, 3, 3 zeros. So that becomes 123,000 as the solution. Not 123. Take note of that. Okay? Then next, we can also look at another example. Let's see what I have here for you. I still have something like this, which says number 4. Correct 241.34 into 3 times 10 raised to the power minus 3, and then everything squared, and then to 4 significant figures. 4 significant figures. You are told to correct this to 4 significant figures. So what would this be? As you can see, our solution, let's see, will be equal to our 241.34 times 3 raised to the power 2, as you can see, times 10 raised to the power minus 3, all raised to the power 2. When you simplify this, you are going to have your 2172.06, and then times 10 raised to the power minus 6. Minus 3 times 2 is minus 6. 9 times this number will give you this. And the result will be equal to 0.00217206. And of course, we can correct this to how many significant figures? 3. So we'll go ahead and correct this to, 4 significant figures. 1, 2, 3, 4. So we have 0.002172. And this is the solution to the problem. Example 5. The radius of a circle is given as 5 centimeters, subject to an error of 0.1 centimeter. What is the percentage error in the area of the circle? You will recall that the area of a circle is calculated using the formula pi r squared. Now, given the error, so we have the error area will now be pi multiplying 0.1 all squared. Then, of course, the area of the circle measured as 5 centimeters radius will now be area of circle will be equal to per times 5 centimeters squared. Therefore, percentage error in the area of the circle will be equal to per times 0.1 all squared all over per times 5 squared, multiply this by 100 all over 1. This will translate your per, we cancel per, and then you will have 0.01 all over 25 times 100 over 1. And this will become 1 all over 25%, or 0.04%. Example 6. Calculate the percentage error in each of the following measurements. A ball is 0.95 meters tall to 2 significant figures. B, a man is 1.25 meters to the nearest centimeter. C, the capacity of a bucket is 12.8 liters to 1 decimal place. D, the speed of an aeroplane to 600 kilometers per hour to 1 significant figure. This is 600 kilometers per hour to 1 significant figure. Solution. Let's say the first one, A. You will observe that 0.95 meters to 2 significant figure, it starts from 9.5, 2 significant figure. The 2 significant figure means to the nearest hundreds. To the nearest hundreds. And the nearest hundred is equal to 0.01. The error, therefore, will be equal to 0.01 divided by 2. And that will be equal to 0.005. So our percentage error will now be equal to the error, which is 0.005, divided by the measurement, which is 0.95. Multiply this by 100 all over 1. And when you do this, you will have your result as 0.53%. That will be the percentage error in this measurement of the height of the ball. Example B. The man is 1.25 meters tall, and 1.25 meters tall is sitting at 125 centimeters, multiplying by 100. And if this is to the nearest centimeters, so the nearest centimeter will be equal to the nearest unit. And then, of course, the error, therefore, will be equal to the unit all over 2, and that is equal to 0.5. Now, our percentage error will now be equal to 0.5 all over 125, multiply this by 100 all over 1. And the result of this calculation will give you 0.4%, or you can say this is 2 all over 5%. Now, the third one is the capacity of the bucket. The capacity is given as 12.8 liters And this is to 1 decimal place. To 1 decimal place. 1 decimal place means that is to the nearest tenth. To the nearest tenth. And the nearest tenth will be equal to 0.1. And so the error in this place will become 0.1 divided by 2, and that is 0.05. So our percentage error, therefore, will now be equal to 0.05 all over the 12.8 multiply this by 100 all over 1. If you calculate this, you will have 0.39% as the percentage error. Then the last example is the speed of an aeroplane is given to us as 600 kilometers per hour. And this is to one significant figure. That is, to one significant figure means to the nearest 100. That is to the nearest 100. And so the error now will be the 100 all over 2, and that is equal to 50. So our percentage error will now be equal to the 50 all over the 600 multiplied by 100 all over 1. Eventually, this calculated, it will give you 8.3% as the percentage error in that speed. Example 7. Complete the table below. We have a measurement which can be referred to here as the true value. We have the approximate value, and then we have the error. Let's take the first one, A. A measurement of 9 centimeters. What will be the approximate value? It means the range of this measurement lies between 8.5 and 9.5. You reduce this by 0.5 and then you increase it also by 0.5. And the error in this case, as you can see, is plus or minus 0.5. B. You have 1.75 meters. What is the approximate value of the range? The range here will be 1.745 and then up to 1.755. You are increasing and decreasing by 0.05. 0.005. So the error is plus or minus 0.00 and then 5. C. You have a measurement of 6,400 kilometers. The range will be 6350 to 6450. Give you an error of plus or minus 50. For 9.8 kilometers measurement, the range of the approximate value will be 9.75 up to 9.85. Give you an error of plus or minus 0.05. E. A measurement of 30.2 units will give you a range of 30.15 to 30.25. And the error here is plus or minus 0.05. This completes the example for this table. Similar cases, you should now be able to know how to get your error in this format. Example 8. A surveyor measures a road as being 69.3 kilometers long. However, there is a minus 1% error in this measurement. What is the true length of the road? Our solution. Since we don't know the true length of the road, we say let the true length be S. And we know that percentage error is equal to the error all over the measurement. That's 100 over 1. In terms of percentage, we therefore have our minus 1% is equal to, or rather, let's take minus 1 is equal to the error, which in this case is 69.3 minus S. Because it is negative, it means that the actual measurement will be greater than the 69.3. Divided by S, and then this is multiplied by 100 to give you the percentage. In other words, we have minus 1 all over 100S is equal to 69.3 minus S. If you solve this, you have your minus 1, or rather minus S, plus 100S all over 100 is equal to 69.3. This gives you 99S equal to 6930 by cross multiplication. Therefore, S is equal to 6930 divided by 99. The result of this will be equal to 70 kilometers. So the true length of the road, which we have called S, is 70 kilometers. Example 9. A student measures a piece of rope and found that it was 1.26 meters long. If the actual length of the rope was 1.25 meters, what was the percentage error in the measurements? Solution. Our percentage error is equal to the error in the measurement, 1.26 minus 1.25, all over the actual measurement, which is 1.25, multiply this by 100 over 1. Now, this will translate to 0.01 all over 1.25 times 100 over 1. Move the decimal point 2 places, so we have 1 all over 125 times 100 over 1. And this will be equal to 0.80% as the percentage error. Now let's take some exercises. And these exercises are adopted from past questions. Question number 1. Evaluate 0.02 times 0.275 divided by 7 times 0.02. Correct to 3 decimal places. And you have the various options A, B, C, D, as you can see them there. Number 2, evaluate 0.21 times 0.072 times 0.00084 all over 0.006 times 1.68 times 0.063. Correct to 4 significant figures. We have options A, B, C, and D. Number 3, evaluate 81.81 plus 99.44 all over 20.09 plus 36.16. Correct to 3 significant figures. The options A, B, C, and D are also there. Question number 4. Express the product of 0.0014 and 0.011 in standard form. We have options A, B, C, and D. Question number 5. Find the value of 0.006 raised to power 3 plus 0.004 raised to power 3 in standard form. We have options A, B, C, and D. Number 6. A stick is 20 centimeters long. A student makes a 5% error in measuring the stick. Find the 2 possible values for the student's measurement. We have option A, B, C, and D. Here are the correct options or answers to the problems, the exercise. Number 1, B. Number 2, A. Number 3, B. Number 4, D. Number 5, C. And number 6, C.